we have to first of all wind up with the applications of differentiation with some physics type of application questions, and then we will get into indefinite integration, which is the next part of calculus for us. So now we are coming towards the end of the calculus section.
Sir, will integration come in our day after tomorrow test?
Yeah, just the very basic part, that couple of formula based things that we learned today in integration. So don't worry, the main thing will be about application of differentiation, and integration is very simple, is formula kind of thing, quite related to differentiation. So basic things will be asked in integration for the test day after tomorrow, and that will be
So you're not audible.
and just check your internet connection. The audio is output is full from my side. The timing of the test then will be informed to you in the group only, don't worry. Normally it is in the morning half around 10 a.m. Yes, Tejas rather. The syllabus will be up to today's session, including of today's session. Okay, so how chain rule is applied in physics type of situations. So for example, suppose a quantity y depends on another quantity x, let's say, such that y is equal to some kind of function of x, okay, and x changes with time t, okay, such that its instantaneous rate of change is this thing, dx by dt. Then to find instantaneous rate of change of y, with respect to t, this is where we apply chain rule concept. We look at application of chain rule. Okay, so for example, before we come to examples, let's see how we execute this chain rule. So y is a function of x. That means dy by dt can be written as dy by dx into dx by dt. This is our chain rule. So further, this will become derivative of fx, because y is equal to fx from above, this one. From that we can see that we can relate dy by dt, that is the instantaneous rate of change of y with respect to t, as f prime x, so the derivative of fx multiplied with dx by dt. So this is the final formula or the method that we'll be applying in these type of applications. So just make a quick note of this, then we'll discuss type of questions in which this can appear.
So done.
Yes, what is your question? Just speak a little bit louder.
So I'm saying done. I wrote the.
Okay. Yeah, Aditya, to answer your question, integration is not tough because it's like the reverse process of differentiation. So if you are familiar with differentiation and doing problems based on differentiation, you will not find it difficult at all. So let's look at an example of this. So suppose we have a situation where we have, let's say, a square plate, like a thin metallic square plate. So three-dimensionally it looks like this. So very thin. So a thin metallic plate is expanding slowly due to rising temperature such that its side length increases at a uniform rate of 0.2 centimeters per minute. Find the rate at which its surface area increases at an instant when its side length L is equal to 10 centimeters. So this is an example of an application question of the above concept. So what is happening is gradually, because of heating and thermal expansion, this is increasing in size. So the surface area is also increasing in size. So we are given that the length, side length is changing at a uniform rate of 0.2 centimeters per minute. So we have to find the rate at which its surface area is increasing. at an instant when the value of L, that is the side length, is 10 centimeters. And by surface area, what we mean over here is total surface area. So how we'll understand this problem is that the surface area, let's say we denote it with the symbol A, it is 2 times L square. And we understand why it's 2 times L square, because A is the total surface area. So it's got both surfaces, okay, the upper surface and the lower surface. For example, if you want to paint this metallic plate uniformly everywhere, so how much area you have to cover with paint? It's not L square, you have to cover 2L square, because both the upper surface and the lower surface have to be covered. So like that.
So we're considering width to be negligible, right?
Sorry, we are considering
The width of the
it's
plate.
to be negligible. It's saying that it's a thin thing, it's a thin plate. So we'll assume it's like a sheet, actually, like a thin sheet which is of square dimensions. Also add that it is square in size. So now we can see that it's given to us that the length is increasing at a uniform rate. So dl by dt is 0.2 centimeters per second, sorry, per minute. This is what is given to us, that the length, the side length is increasing at uniform rate of 0.2 centimeters per minute. So from that, what we have to do is we have to find the rate at which the area is changing, okay, at an instant when L is equal to 10 centimeters. This is what we have to do. Okay. So the information that we have is this information, that we know the relationship between total surface area A and L. So we know that, okay, this is given to us additionally in the question. And this is also given that the value of L at the instant when we want to calculate is this. From this, now what we have to calculate, we have to calculate this quantity. Okay. So what we'll understand here, Ajay, try out this question. We'll discuss in a moment. So just try to apply that concept that we saw above, okay, that if y depends on x, okay, and x is changing with time, okay, then dy by dt will be equal to dy by dx into dx by dt, this chain rule application. So here I've written it for general parameters x and y with respect to time. Now you apply this over here. You apply this to this situation. Think yourself how you'll apply it. Okay. We'll discuss. Okay, Harsh, what is the unit in which you're getting it? The rate of change of area? Because now it's a physical quantity, so we have to also express it in units.
Centimeter square.
Per?
Sir, centimeter square per minute.
Per minute. Okay, that's correct. Very good. Yeah, very good people. You are getting the answer now. So I'll just show the method for everybody else also. So total surface area here we are writing as a formula as 2L squared. So basically that is showing us that the area is some kind of function of L. Okay. And we want to find dA by dt, where we are given the value of L and we are given the value of dL by dt. This is given and the value of L is given. So what we have to find is this. So we have to use this chain rule concept. Okay. So dA by dt will become dA by dL into dL by dt. This is a chain rule step. Now we'll substitute this A as a function of L over here. So we will get this as 4L, right, into dL by dt. And now we can just directly substitute the values given. So this thing can be substituted and the value of L at that instant, this can be substituted. So this will become 4 into 10 centimeters into 0.2 centimeters per minute. So it will become 8 numerically, and you can see the unit will be centimeter into centimeter per minute. So centimeter squared per minute. So the area is increasing at that moment at the rate of this much. So this is the rate at which A is increasing. At the instant when L is equal to 10 centimeters. Okay, so this is a very important type of application of differential calculus.
Sir, could you just tell me how the surface area came 2L square?
Yeah, can you repeat the question, better?
Sir, how did the surface area come 2L square?
How to?
How did the surface area came 2L square?
Just hang on a minute, but I can't hear you. I'll just change my speakers. Yeah, can you repeat what you're saying?
Sir, I was saying that how did the surface area come 2L square?
How did the surface area come 2L square? That we've seen earlier, that it's a square plate, no? So square plate ka, what is the surface area of one face, the upper surface? It is L into L, no?
Yes.
L square. So the total surface area is the upper face plus the lower surface put together. So that's how much? 2L square.
Sir, but it's just single plate, right?
That's what I explained better. A plate has two surfaces, na, and an upper surface and a lower surface. Like for example, if you want to apply paint on the surface, how much surface area you have to cover for the whole plate? You have to cover 2L square, no?
Yes.
Right? So because the question is clearly saying that it's total surface area, not the surface area of one side, but total surface area. No? So we have to take it as 2L square.
Yes, sir.
You got it understood?
Yes, sir. Thank you.
Okay, okay, good. Okay, now let's move on to another. Achha, so I'll just wait for you to go through this once. Okay, let's move on to another example. So now we have a situation like this. We have a solid sphere. Of radius capital R is slowly expanding such that its radius R increases uniformly with time. Again, at a given rate. So let's say this time the rate is equal to say 0.5 centimeters per minute. Now at a certain instant, its radius is R equal to 10 centimeters. You have to find the rate at which its diameter is changing. Then the rate at which its surface area is changing. And finally, the rate at which its volume is changing. We can even add one more part, the rate at which its density is changing. Okay, so same type of concept, same method, just try it out. Okay, so I'm first of all just relating the formula that we'll require. Okay. So what is the relationship between each of these quantities which are asked? Let's say
The
diameter.
diameter 2r.
Yeah, those formula. Diameter, suppose we write as d, it's 2 times the radius. Surface area, let's say we write as a or whatever. So that is 4 pi r square.
Where?
Volume is
4/3 pi r
Like 3
cube.
pi r cube.
pi r cube. Very good. Okay. And density So let's say we use capital D for diameter, so we can use small d for density. So density का क्या formula हो जाएगा? Mass upon volume.
Mass volume.
That is 3m upon 4 pi r cube. We can also write, and we understand here that mass is not changing. M is constant. Because while it's expanding, it's not like material is being added. We're talking about thermal expansion, let's say over here. So the density reduces as the volume expands. The mass does not change. So that's, let's say, given in the question as an assumption. Assume its mass is constant. You can have a situation where mass is changing, like, you have, let's say, a snowball, and because of snowing happening, so continuously snow is getting added to it. So in that case, the radius is changing because more mass is getting added. Layer after layer of snow is added to it. So in that case, mass would not be a constant. But here, let's say we are assuming that kind of situation where the expansion is happening because of like thermal expansion. You are heating the metal of the sphere, so it's expanding. But you're not changing the mass, so mass is constant. Okay, so just send me the answers as you're working it out. Yes, very good, Aruchi. Correct. All three are correct. A, B, and C. Now work out part D also. Yes, Vedant, but the unit will be in centimeter per second for the first part. The value is correct, what you said.
But per second, not per minute.
Yes, second for the second part is also correct.
So it's minute, right? Not seconds. So
Yeah,
density
it's
will
per
be
minute.
1 centimeter per minute.
Yes, it will be, A part's answer will be diameter is increasing at the rate of 1 centimeter per second. So diameter is 2 times radius. So that means the rate of change of diameter with respect to time is rate of change of 2r with respect to time. So that is 2 times dr by dt. We can even do it directly like this. Likewise, the surface area is 4 pi r square. So rate of change of surface area will become like this. Okay. Eight pi r, right, into dr by dt. So at that particular moment when we are calculating, r is 10 centimeters. So 8 pi multiplied by 10 centimeters multiplied by the rate at which that was changing was 0.5.
So sir, 45 centimeter square by minute.
Correct. Very good. 40 pi, correct, centimeter square per minute. My mistake. This should also be per minute. And now very similar process for volume, but only you'll be differentiating r cube. So 4 by 3 pi is a constant into differentiation of r cube will become 3r square into dr by dt. So that is 4 pi r square dr by dt. So that here will become 4 pi into 10 centimeters square into 0.5 centimeters per minute. So this should become 200 pi centimeters square per minute. Is this correct?
Yes, sir.
Yes, sir.
Now see, the important thing is all these are coming with plus sign. So area is increasing with time. You can see diameter is increasing with time. Same with volume. But density will be decreasing with time when we calculate. Okay.
Sir, is my answer correct for the D part?
Sorry, come again, beta. What was the question?
Sir, is my answer correct for the D part?
I'll just check. I'll just check it. Just give me a moment. No, no. Okay, you have to relate it with the formula directly now. Okay, density is inversely proportional to volume. So use that, or inversely proportional to r cube. You can use that also. Yes, once that's correct. You can also write the surface area and volume in terms of diameter instead of in terms of radius. You'll get the same
That then,
result when you.
so for that, then we'll have to convert it back, right? We have to
Yeah,
multiply
you'll
it,
have
right?
to convert it back. You have to write the diameter as double of radius and
Okay, because then I was like getting a different answer with diameter.
So I'll just show you with one example. For example, the surface area in terms of diameter, what we can write it as 4 pi into diameter by 2 whole square, correct? So it will become pi d square. Okay. So rate of change of surface area with respect to time will become rate of change of surface area with respect to diameter into rate of change of diameter. So this term will be now differentiation of pi d square. So it will be 2 pi d into this rate. Now you see, at the moment when we are talking about the radius is 10 centimeter, so the diameter is 20 centimeters, and rate of change of diameter we had seen was 1 centimeter per minute. So you see, you're getting the same thing, 40 pi centimeter square per minute. So there's no extra effort really. It's the same thing. Just you have to convert the formula in terms of diameter.
I'd not convert the formula itself.
So that's what we're doing. Okay, now let's come to the last part. So I'll just give you a bit of a hint because nobody sent me the answer for D part except for one person. Okay, so density, suppose I use this formula, mass by volume. Okay, then the rate of change of density. So this will look a bit odd the way I'm writing it. Will be rate of change of density with respect to volume into rate of change of volume. Okay. So this thing is going to be rate of change of m by v with respect to v into dv by dt. So next step, this will become what? M is a constant, it comes out, and differentiation of 1 by v with respect to v. So that is minus 1 by v square. So the rate of change of density will be a negative quantity because the density will be decreasing, and it will be given like this. And now we can substitute that at that particular moment, the volume is how much? 4 by 3 pi r cube. So it is 4 by 3 pi into 10 centimeter cube. And dv by dt, we had just seen was above, was 200 pi centimeter square, sorry, centimeter cube. I've written the unit of this wrong, okay? This should be centimeter cube per second because it's can see above that we have centimeters square multiplied by centimeters per second. So the correct unit here is centimeter cube or cc. Also we can write it as, okay. So yeah, so the rate of change of volume when we substitute the value from above, it will be like this. So this is one way of doing it. Okay, so substitute and try it out and see what value you're getting. Another way you can do is you can also express density as this. Okay, and then you can use the fact that rate of change of density with respect to time will become rate of change of density with respect to radius into dr by dt. You can also use this method. Here I have used this method. Okay. And also when you calculate this rate, it will come out to be a negative quantity, which tells you what that the density is decreasing with time. While the other three quantities that we saw, the diameter, surface area, and volume, they were all three were increasing with time. This one is the one which is decreasing with respect to time. So actually to get the numerical value of this, we have to know the mass also. So let's say in addition to this, I'm also giving you the mass of the sphere is given to us. So the mass is, let us say, so just add one thing to the question. Just a moment. So just over here, let's assume its mass m is equal to, let's say it's 4 kilograms is constant. Okay. So here we'll also add that value of mass.
Sir, hello.
Yes, Vedant, what is your doubt, beta?
Sir, if we differentiate density with respect to radius, would we have to use the quotient rule like that?
No, you don't have to use quotient rule, no, beta, because radius is in the denominator with a power of 3. No? So just bring it to the numerator r to the power -3, na?
Okay, yeah, because everything else is a constant already.
Because there is no other in the numerator. You have a constant, na? M. That's why, yeah.
Yes,
So you
sir.
will not need the quotient root. Got it? Na?
Okay.
Okay. So anyhow, let's see the value with this method first, right? So
the constant we are getting is 3 by pi, right? If we take mass as 4 kgs. Okay.
So 4 kgs, okay, divided by volume ka square ho jayega, so that will be how much? So the volume at this point of time is how much? It is 4000 pi by 3 centimeter cube. Okay. So square of that. So imagine that's like 4000 pi by 3 squared. Okay, and this is in now centimeter cube. Okay, into this quantity, dV by dt, the rate of change of volume, which is 200 pi in centimeter cube per second. So actually, just a minute, the centimeters cube is inside this bracket because you're squaring the volume. So it's in centimeter cube and the whole thing is squared. Okay. So we will have -4 by 16 into 10 raised power 6 pi square. Okay, this 9 will come in the numerator. Okay, and then into 200 pi. And now what the unit will become? See, it will become kilogram per centimeter cube second, like this, because it's centimeter to the power 6. So it's like this. So it's becoming -9 by 4. Okay, pi. No, -9 by 2 pi. So -9 by 2 pi into 10 raised power, how much will be left now? 4 minus 6, so -4 kilogram per centimeter cube second. Okay. So now we will convert this kilogram into grams so that we can write it in gram per. So you can write it as 9 by 2 pi into 10 raised power -4 into 10 raised power 3 to convert this to gram per centimeter cube second. So this will become now like this, -9 by 20 pi. Okay. Gram per centimeter cube per second, we can say. The second is in the denominator, so you can think of this unit basically like gram per cc per second. And the minus sign is to show you that the rate at which the density is changing is a negative rate. So the density is reducing at the rate of 9 by 20 pi grams per cc per second. So we can see that density is reducing at the rate of 9 by 20 pi. But again, I made the mistake of writing it second. Gram per cc per minute it should be actually. So wherever I've written second, we have to replace it with minute, because here itself this was wrong. This is per minute now. So wait, I'll just make that correction and then we'll see the whole thing again. Okay, so now I'll show you in a minute that we can get the same kind of result by using the relationship with radius also. Okay. Now let's also work this out by the second method here, where we can reference it to the radius. Okay. So the density is 3m upon 4 pi r cube. So the rate at which the density is changing will become d by dr of this thing into dr by dt. So 3m upon 4 pi comes outside. Differentiation of 1 by r cube will be minus 3 by r to the power 4.
Yes, sir.
Into dr by dt. So here we are just using this relationship, that differentiation of 1 by x cube with respect to x, that is differentiation of x to the power minus 3, that is minus 3x to the power minus 4. This little thing we are using here. Okay. So this becomes minus 9 by 4 pi, right, m upon r to the power 4 into dr by dt. So this will actually be easier to handle. Okay. So 9 by 4 pi into 4 kilograms, okay, into the radius was 10 centimeters, so to the power 4, okay, into the rate of change of radius was how much? 0.5 centimeters per minute. So hopefully it should give us the same value unless we made some mistake. So let's see. So 9 by 4 pi into 4 into 1000 I'll do, because I'll convert this to gram. Okay. Divided by 10 raised power 4 centimeter to the power 4, okay, into 0.5 centimeters per minute. This is giving me minus 9 by 2 pi into 1 by 10. I've taken the 0.5 as half actually, so that's how I got this. Okay. Okay, so I'm getting this in gram per cc per minute. That's correct. So this type of calculation is lengthy. It requires a lot of patience. Okay. So you should not worry about how much time it's taking to solve and all that. Just be sure that you're learning about how we are applying calculus over it, how we are relating the rate of change of two different quantities. We have, from the rate of change of radius, we are relating how the density is changing by understanding what is the relationship between density and radius. So that is the physical application of chain rule. Okay. One thing is related to another. So here density is related to radius, and radius is changing at a certain rate. So how we can use chain rule to find the rate at which density is changing?
Sir,
Yes.
so at the second last step, you wrote into 0.5, then afterwards, like into 1 by 10, like did
Oh, actually,
0.5.
I'll tell you what I've done. I've written 0.5 as half, and then I've solved everything. Okay, so the 4 and 4 I've cancelled.
Oh, okay, understood.
And then this I've cancelled. So there's a 10 in the denominator, and 0.5 I've just written as half. Okay. And then I just
Okay.
put the units. So
Okay.
gram upon centimeter to the power 4, but into centimeters. So that's how. Okay, so people, I think we are all clear with this question, right? So like this density part was like a very extreme application because we had volume in the denominator or R cube in the denominator. Normally at our level, things will be easier. Like the earlier parts you saw volume, rate of change of volume. So we just have to differentiate R cube or rate of change of surface area. So you'll find few questions of that type in exercise 3 of your module. There are 4 or 5 questions like that. Please try them out in the next couple of days before the test coming up on Sunday. So for the test, like before I get into integration, the most important thing for the test will be your applications of differentiation by chain rule, which we have been discussing in the last lecture and all, last few lectures, and your application of like basics of differentiation, product rule, quotient rule, all those things before that. Of course, you should know all the formula of differentiation of x to the power n, differentiation of the trigonometric function, sine, cos, tan, all that, exponential, logarithmic. So all that you should not get confused with during the exam. Okay, so make sure that happens. Then the properties, the product rule, the quotient rule, all that, and chain rule, and then finally application problems of this type. This is going to be the most important part. There will be a few questions on integration, but that will be very easy. And now we're going to do the basics of integration, and you'll understand why I'm saying it's very easy, because it's like just the reverse process of differentiation. Okay. So let's begin with the second part of calculus in terms of operations. But it's not like it's half of calculus, it's much less than that, because differentiation is the big part.
Excuse me, sir.
So integral calculus. Differential calculus is one type of operation, integral calculus is another operation. So the first type of operation we will study in this is called indefinite integration. So indefinite integration is a simple operation that is, or you can say that can be applied to a function, let's say fx, to calculate something called its antiderivative. Now I'll explain just now what is antiderivative. And typically we denote the antiderivative with the symbol capital I. So what we mean by antiderivative is that if Ix is the antiderivative of fx, it implies that differentiation of Ix will give us fx. That's the simple meaning of antiderivative. So when I explain it with an example, it will become clear. So suppose fx is 2x. Okay. Then its antiderivative, let's say Ix. Now that is such a function, it is such that differentiation of Ix should give me fx, or it should give me 2x. Okay. Now can you tell me what is Ix? Just think and tell me. Whose derivative is 2x?
X square.
X cube.
X square. Okay, but now I'll just say instead of x square, if I tell you x square plus 5, that's also correct.
Yes, sir.
Sir.
Because
Yes,
derivative
sir.
of a constant is 0.
Constant.
0.
Okay, so that's how we'll understand now that two things. That one is that we know that differentiation of x square is 2x. Okay, and second thing is we know differentiation of any constant is 0, where c is a constant. Okay, so therefore putting both these points together, we'll understand that over here that the antiderivative is not just x square, it is x square plus any constant, where c could be any numerical constant or any real number. Okay. Because now we know that, okay, if we differentiate x square plus c, we'll get 2x. Okay. So therefore this Ix equal to this is the antiderivative of 2x. Okay, so we'll develop a systematic method of doing this. This question we have done by guesswork. Okay, but we'll develop a systematic formula for it. But you'll understand that it's very easy to get this, because you are familiar with differentiation through lots of problems by now. Okay, and many times you've applied the different formulae, properties, and all that of differentiation. So now this indefinite integration is just a process where you're reversing that process, those steps of differentiation. So it's not going to be difficult to work it out at all. Okay. So anyhow, just make a quick note of the points over here, and particularly go through this example I've given you and try to understand the logic of this one. Okay. So through that, you once again make sure you're clear with the term what is antiderivative. If I say fx is antiderivative is ix, it means that if I differentiate ix, I should get fx. Fx's derivative comes by differentiating fx, but fx's antiderivative comes by finding such a function. That function's derivative should be fx.
Sir, can you scroll down a bit?
Yeah, I'll scroll down. Just wait a few seconds. Let people.
Done, sir.
Oh,
So just a second.
Sir, one
yeah.
minute.
Simple substitution.
So done.
Oh,
Done, sir.
yeah. Okay, so now the first thing we'll understand is that the symbol for integration. This symbol is called the integration symbol. And how to integrate a function? So to integrate a function fx, okay, we operate integration of fx, but then that is written with dx. Okay, so that dx is written to show that we are integrating the function fx is being integrated with respect to the variable x. Okay, so that is where this comes in. It shows us that it's, and this is of course the integration symbol. So for example, if we write integration of, let's say, ax square plus bx with respect to x. So here it is understood that the variable of integration is x, because we are integrating with respect to x. So hence it's an implied thing that a and b must be constants. But similarly, for example, if we are integrating, let's say, some quantity h with respect to the variable t, so it means that the variable of integration is t. So that automatically implies that h must be some kind of function of t. Okay, the quantity h, it must be dependent on t. So this capital H, whatever it is, must be a function of t. It should not be a function of some other variable. Then we can't integrate it. So this is just about the symbol. We make a quick note of this, then we will come to actually how we do the integration.
Sir,
Yes.
sir, can you explain this part again, HDT, where you wrote?
So see, we have written the integration symbol, then we have written some quantity, and then we have written dt. So whatever we write the d with, that is the variable of integration. Like when we differentiate, we write d by d something. So suppose we write d by d theta, then whatever we are differentiating, it should be a function of theta. If we write d by dx, then whatever we are differentiating, let's say f, it should be a function of x. Otherwise, it doesn't make sense, right?
Yes, sir.
So like that, now integration ke liye bhi, when we write the operation, we have to specify which variable we are integrating with respect to. So that is why the term dx is written, or over here the term dt is written. And whatever we are integrating with respect to dx or dt, that has to be a function of that particular variable. So if we have written dx, then we should be integrating something which is a function of x. If we have written dt, it should be a function of t.
Oh, okay, understood, sir.
Understood? So it's so this is just a symbol. Okay, now we'll come back to how to do the integration also.
Done, sir.
Yeah.
1 minute.
Yeah.
Sir, 1 minute.
Yeah, I'm waiting. Okay. Okay, done.
Sir, just a
Yes,
Okay.
done.
done, sir.
Okay, good. So now when we integrate a function, what the operation results in, it results in giving us the antiderivative. Okay. So the you can say, what is the definition of the operation? So when we do this integration, the result it gives us, or the output it gives us, is the antiderivative. So that implies that the quantity that we get, if we differentiate that, we will get the original function which we integrated. Okay. So the output of the operation is the antiderivative, and since the antiderivative always has an unknown constant, C, therefore it is called indefinite integration. This operation is called indefinite integration because it gives us an indefinite answer. So now you can just include that example that I told you, that integration of 2x is going to be x square plus c. Why? Because differentiation of x square plus any constant you can think of, including 0, is 2x. And you can include another example. Integration of cos x will be sin x plus c. Why? Because we know that the differentiation of sin x is cos x, and the differentiation of any constant is 0. Likewise, for example, you can see that the integration of 4x cubed, suppose we have. So that is x to the power 4 plus. Same kind of reason, because you know differentiation of x to the power 4 is 4x cubed. So you can also understand the relationship between a given function and its antiderivative like this, that the function gives the antiderivative by doing integration. If you integrate the function, the output of that is the this. Whereas the antiderivative can give the function again by applying differentiation. So they are reverse operations of each other. Like square root and whole square are reverse operations of each other. If you square 2, you get 4, and then if you take square root of 4, you get 2 back. So like that, they are inverse of each other or reverse of each other as operations.
So
Yes.
So in every every time when we do integration, we'll always get a constant.
Yes, we will get an unknown constant term. And that is why the operation itself is called indefinite integration. Okay. Now later we will see that when we apply this in physics problems, that if there's some other condition that we know, apart from the fact that we are calculating antiderivative, we know some other condition, then we can find the value of that constant. But without any other given condition, we cannot find the value of the constant. It's an
Sir, so could you repeat again what is dx over here?
dx is to show us that the variable of integration is x. Okay. So for example, if I've written like 4x cubed dx, No, last one. So it means I'm integrating the function 4x cube with respect to the variable x.
So it only denotes what variable we are using here.
Exactly. What variable we are integrating the function with respect to, it denotes that. And the function should be of the same variable. Like we cannot integrate, let's say 4t cube with respect to x. It will not make sense. 4t cube dx, where t is some other variable, x is some other variable. That operation only will not make sense.
Yes, sir.
Okay, so this is clear, people, written down.
Yes, sir.
Yes, sir.
Okay, so now having understood this operation itself, we come to the formulae, which will be very easy to follow because they are just like the reverse process of differentiation. Okay. So we'll see that it follows a pattern. Just now we saw that if you differentiate x square, you get 2x. So that means if we differentiate x square by 2, we'll get what? X, because I'm just dividing by 2 on both the sides, right? This makes
Yes.
sense. So that means what this is telling me now, that if I integrate x, I should get x square by 2 plus c. Now, c is just there because its derivative is 0. Now similarly, you notice that if you differentiate x cube, you get 3x square. So now to get rid of the 3, just divide both sides by 3. Okay. So put a division by 3 here, division by 3 here. So this will show you that differentiation of x cube by 3 is equal to x square. So that means integration of x square is what it is, x cube by 3 plus c. So like that, randomly, if you think of any power now, like let's say I think of x to the power 10. So you see I'll get 10x to the power 9. So now I'll divide both sides by 10. So this will now show me that differentiation of x to the power 10 by 10 is equal to x to the power 9. That shows me that integration of x to the power 9 is equal to x to the power 10 by 10 plus c. So noticing this pattern now, I can, like, though I've taken the pattern only for whole numbers, powers is whole numbers, but we can see that we get this kind of a general formula, that integration of x to the power n is given by the formula x to the power n plus 1 upon n plus 1 plus c. So this becomes the general formula. Okay. But here, one thing important is that n is any real number except, there's a notable exception, except for n equal to minus 1. Okay. Because minus 1 will give you 0 in the denominator, which is not defined.
Possible. Yes.
So with the exception of n is equal to minus 1, we can use this for anything. Okay.
So, sir, we cannot integrate x raised to minus 1 at all.
No, there's a different formula for it. I'll come to that. Okay, so you have to remember that one as a separate one. But for any other power, this will do. Okay, so this becomes the general formula for integration of x to the power n type. You can see it's like a kind of reverse thing of what we did in differentiation. When we wanted to differentiate with respect to n, we multiplied by n and reduced the power by 1. When we want to integrate x to the power n, we divide by n plus 1 instead of multiplying by n, and we increase the power by 1 instead of reducing the power by 1. So that's how they are inverse operations of each other. We will discuss about the exception also, but first we'll discuss some examples. Okay. Yeah, Rishikesh, just write down this formula now, and when I explain it with examples, this will become clear. Okay. Okay, very good, Rishikesh. Yes, for n equal to -1, we have a different rule. I'll come to that. So let's see some application examples. Don't worry about n to the power -1. I'll come to that. Okay. So I want to integrate, let's say, x cube. So I'll just use this formula: x to the power n plus 1 upon n plus 1 plus c. So that is nothing but x to the power 4 by 4 plus c. Now we can always verify that this function which I have written, x to the power 4 by 4 plus c, is the correct value of antiderivative for the function fx equal to x cube. Which is why now we should never make a mistake in integration, because we can always check our answer ourselves. So if it's the antiderivative, then its differentiation should give me fx. So let's check. So just mentally differentiate this term. So see, 1 by 4 comes out, differentiation of x to the power 4 is 4x cube. The differentiation of a constant is 0. So obviously it's x cube. So that's correct. So there's no chance of making a mistake. Okay? Because even if I made some calculation mistake and I just happen to check that differentiation is giving me the original function or not, that will tell me that, okay, I made some mistake. Okay. So let's look at another example now. So suppose I have integration of 1 by root x. Okay. So this will have to be written as integration of 1 upon x to the power half, and then we'll bring this to the numerator. Okay. Now we can apply this formula because we've written it in the type x to the power n. So basically, first we have to express this. Express the function fx as x to the power n. Then we will apply the formula. Next step. Okay. So when we apply the formula here, we will get x to the power minus half plus 1 upon n, or minus half plus 1 plus c. So that is telling me that this should come out to be 2 root x plus. Now you can always verify yourself that this is the correct antiderivative of this one. In fact, I have skipped a step here, so let me just write it fully for you. So this will become x to the power half upon half. So it will become 2x plus c.
So
Yes.
can you just scroll up?
Yeah. But see, these are just examples to understand the logic of this formula. Okay. Main thing is this formula now, and we are applying it in these two examples below.
So
Yes.
can you explain this formula again, where you wrote d into x raised to power n by dx equals to nx raised to power
This
n?
one, this formula, how it came, na?
Yes, sir.
See the pattern here, na? X to the power 1 का integration में क्या आ रहा है? X to the power 2 by 2. X to the power 2 के integration में क्या आ रहा है? 3 by 3. X to the power 9, x to the power 10 by 10. So what is the pattern we notice? X to the power n plus 1 upon n plus 1.
Answer this formula where you wrote on the left hand side.
On the
above
right hand
this.
side.
Yes, sorry, right hand side. Yeah, d by dx raised to power x.
This is to the differentiation formula, na? This is the standard formula of differentiation. So this is what
yes,
shows
yes.
us that integration is the reverse process of differentiation. Na? Because when we differentiate a power of n x, we multiply by n and reduce the power by 1. So the reverse of that operation is such that when we integrate, we divide by n plus 1 and we raise the power by 1.
Okay, sir.
Okay. Now, once we've understood the formula, like we have to just learn how to apply it in different situations like this. Okay, so note down this example and then, I mean, these two examples, then work out these next values. Okay. Okay, so try out these 4 examples and just send me the answers by text. I'll verify for you. It's the same process by which we have done the 2 examples above. It's application of the formula above for x to the power n integration. Okay, very good. Vansh, Vedant, Rishikesh, correct answers. Just once you have to remember to add the constant C. So first we'll express this as x to the power n by bringing x to the numerator, and then we'll apply the formula. So this becomes minus 1 by x plus. You can always verify this. If you're having some doubt after doing the question, you can always verify whether we have solved it correctly or not. So differentiation of minus 1 by x is minus 1 into minus 1 into x to the power minus 2. So that's 1 by x. So that's fine. So you can also write this as this, but actually it makes no difference, okay, because this using this.
Sir, in the second term, can we write it as 2 by 3 root of x cube plus c?
2 by 3 root of x cube. Yeah, we can write. Let's go. So you can also express it this way. This only, no?
Yes, sir.
Yeah. Okay, let's come to the third one. So x square root x. So in this we'll express x square root x as x multiplied by x to the power half. Sorry, x square multiplied by x to the power half. So 2 plus half. So that is x to the power 5 by 2. So we'll first have to do a bit of algebra and reduce it to a single power, and then we can apply the formula of integration. And therefore this becomes 2 by 7 x to the power 7 by 2 plus c. And now again that x to the power 7 by 2, you can express it in many different ways. For example, you can express it as x cube root x, or like the previous one, you can express it as square root of x to the power 7 also. Let's come to the final one. Yeah. So dx upon this is cube root of x. So as you know, this thing is called cube root x. So it's x to the power 1 by 3. So bring it to the numerator, x to the power minus 1 by 3. Then apply the formula. This will become 3 by 2 x to the power 2 by 3 plus c. Or you can also express this as 3 by 2 into cube root of x square plus c.
Sir, in the last one, can you please show how to verify it?
Which one? Last one, show what?
How to verify that answer?
Acha, differentiate it. Na? So if you differentiate this thing, differentiation of 3 by 2 x to the power 2 by 3 plus c. So 3 by 2 comes outside. Differentiation of x to the power 2 by 3 कितना हो जाएगा? 2 by 3 into x to the power 2 by 3 minus 1. Because differentiation of x to the power n, you have this formula, na? Nx to the power n minus 1. Got it now?
Yes, sir. Thank you.
Okay, so people hope these questions are clear. So this is the basic thing in integration. Now, few things to keep in mind. The exception case, first of all. Integration of dx by x, or x to the power minus 1 dx, that is x to the power n with n equal to minus 1 in this case. Okay. This is given by a separate formula, natural log of x plus c. And the logic of this is very simple, because we know that differentiation of natural log of x is 1 by x. Okay. So therefore, obviously, integration of 1 by x is ln x plus c. So this is the one exception that you have to remember for that x to the power n rule. And along with that, we have integration of sin x is minus cos x. Okay. Some more formulae. Integration of cos x is sin x plus c. Again, the logic of this I've already explained you, that differentiation of sin is cos, whereas differentiation of cos is minus sin, hence the minus sign comes here. Okay. Then integration of tan x is given by a somewhat more complicated formula, which is natural log of sec x plus c. Now again, you can understand this by doing differentiation. If you differentiate natural log of sec x by using the chain rule, you will see differentiation of log is 1 by sec into differentiation of sec, which is, so you get tan x. So just note down these additional formula and we'll discuss more.
So the differentiation of minus cos x becomes sin x, positive sin x.
Differentiation of cos x is minus sin x, no? That's
Yes,
why
sir.
that's why integration of sin x becomes minus cos x. Understood?
Okay.
Hello, sir.
Yeah.
So could you just explain this once again? I had some network connected issues.
Okay. So see, you know that differentiation of log x, ln x, is 1 by x.
Yes, sir.
So integration of 1 by x, just reverse of that, it becomes ln x plus c.
Huh.
Okay. So now by that similar kind of logic, you also have for sin x and cos x. Differentiation of sin x is cos x. So integration of cos x becomes sin x. But differentiation of cos is minus sin. So integration of sin becomes minus cos. So there's that reversal because of that.
The जो ऊपर वाला method है, that's how we can represent that -1 power.
Yes.
Okay.
So,
Yes.
can you explain the integration of tan x where you wrote ln sec x plus c?
Yeah, see, I told you that one is a little bit more complicated, because what happens in the case of that differentiation of, rather integration of tan x is, it's a formula which involves application of chain rule. So you know differentiation of sec x is what? It is sec x tan x, no?
Yes, sir.
That formula you're familiar with. So now if you differentiate ln of sec x, you'll have to apply the chain rule thing. So differentiation of ln is 1 by, no?
Yes, sir.
That's how we get, see, where I've shown you the justification of that. The differentiation of ln sec x will be 1 by sec x into differentiation of sec x. So it's 1 by sec x into sec x tan x.
Oh, okay.
So that's what shows you that why that formula works. Okay.
Okay, sir.
Okay, so these two formulae are clear now.
Yes, sir.
Okay. Now, just like tan x's integration is a little bit lengthy, like that, the other ones, integration of cosec x is given by a rather lengthy formula, minus ln of cosec x plus cot x. Okay. Now you can do this verification yourself later when you're revising through this. By chain rule application, you can see. Similarly, integration of sec x is
plus c also, right?
yes, of course. Yes, thanks. So ln of sec x plus tan x plus c, and the final one, integration of cot x. We can write it as ln sin x plus c, or we can also write it as minus ln cosec x plus c.
Done, sir.
Okay. So out of this, like, what is going to be really important for us is these two formulae. The rest of them are not going to be so important in our applications in physics, but you should know them. Okay. And exponential function also, e raised power x is e raised power x plus c only. This is the easiest because you know that differentiation of e raised power x is e raised power x. So therefore, integration of e raised power x is also e raised power x.
Done, sir.
And finally, you have properties which are very similar to properties that you have learned in differentiation. So integration of a constant will become a linear function like this, because we know that differentiation of a linear function like this is a constant. So here k is a constant. This is the first of the three properties. So for example, if I say integration of 3 dx, so this will just be 3x plus c. Now likewise, integration of a constant multiplied by a function, just like differentiation, you can take the constant outside and integrate the function. Okay. So example, you want to integrate, let's say, 5x cubed. So just take the 5 outside and integrate this. So 5 by 4 x to the power 4 plus c. This becomes your answer. Or you want to integrate, let's say, 2 sin x. So this will become minus 2 cos x plus, because the integral of sin x is minus cos x. Okay, and then we come to the final property with which we'll complete this part of integration, is distributive property, similar to what we've seen in differentiation also. If we have the sum of two functions So that will become the sum of their integrations. Or if it's the difference, then it will become the difference of the integrations. So a simple example, if we are integrating, let's say, x square plus x plus 3. Let's make this more interesting. Let's make it x square plus 3x minus. So this will become integration of x square plus integration of 3x minus integration of 2. And further, for this middle one, we can take the 3 outside, and the constant, we can combine the constant for the 3 and write it like this. So this is like a combined constant that we write always. We don't write separate constants like C1, C2, C3, because the sum of 3 constants is also a constant. So we just write as a combined constant. So we'll take this down and just, as we conclude, try this question. Okay, so just quickly work out these 2 questions and send me the answers. Then we'll wind up for today. Just a minute, I'll bring the white screen back on. Yeah. So what about the first question? Got it, everyone?
Yes, sir.
Okay, very good. So you have whole squared this first, right?
Yes, sir.
Yeah. So this becomes x square plus
2x
plus
plus 1.
1. And then you use the distributive property. So this one's integral becomes x cubed by 3. This one becomes 2 into x squared by 2. This one just becomes x and the combined constant. So our answer becomes x cubed by 3 plus x squared plus x plus. Now similarly work out this one. So it will just do a bit of algebra to separate out the two terms, right? And then from this step onwards, you can again apply the distributive property. So you can even take 2 root x common.
X square by 5 plus 1. Plus
Yeah.
8.
We'll write it like this or this is fine. So it's quite simple, really, integration. You have to just make sure that you remember the formula for integration of x to the power n. Remember the exception case of ln x, integration of 1 by x is ln x. And then sine cos in particular, but the trigonometric functions. And then the properties. Properties are very obvious. Okay, so when you do few questions, you understand that. Okay. So with this, we complete the basics of integration, and this is what you'll require for the test coming up on Sunday also. Yes.
Sir, I had a doubt on the solid example which you gave just before. Sir, in that minus c should come.
Which one, beta?
Sir, before you gave these two.
This one, no? Yeah. See what's happening now, beta. This is a combined constant. So actually, if I solve this integral, this will give me x cubed by 3 plus some constant, let's say c1. This will give me 3 by 2 x square plus some constant c2, and this will give me minus 2x plus, actually we'll write it as plus only, no? Because the constant can take any value, no? It can be negative, positive, whatever, right? Then what is happening?
Sir, we have 3 different values of the constant, so we are taking that as common.
We have to write that as a combined constant. Okay. Now this combined constant could be any real number, no? So it includes negative values.
So, but sir, here we have 3 different values of the constant.
No, it's not. We don't have values of the constant. No, it's an unknown constant. See, C1 can be any real number, C2 can be any real number, C3 can be any real number. So this sum is also any real number. No?
Yeah, okay, sir.
So that's why we combine the constants. Understood? No?
Yes, sir.
Okay. Yes, somebody else also had a doubt?
So till trigonometric integration part, it will come in the test, right?
Only sine cos, beta. Simple one, sine cos. Huh?
Okay, only sine and cos.
Sine and cos. Just remember the formulae and the properties. Okay.
Okay, sir.
Okay. So that's it for today's session, people. Wish you all the best for the test coming up also. Okay. Make sure you revise properly in the next 2 days. If you have any doubts and things, you can send me messages on WhatsApp also with the questions. I'll help you out with them.
Thank you, sir. Bye, sir.
Bye, sir. Thank you.
People,
Thank you, sir. Bye, sir.
Bye.